physics and beauty in quantum physics. As I have nothing to say about this theme, it's better that I will give the word to Sabrina, but first I want to welcome you, and Sabrina Maniscalco comes from Turku University, where she is a professor in theoretical physics. So,
thank you very much. Thank you. Well, first of all, I should say that it's quite exciting and a new experience for me to talk about beauty in quantum physics. I've never talked about this topic before, though obviously I have experienced it many times. And I hope that I will be able to convey some of the ideas and some of the problematics also related to language and related to understanding quantum physics. And I think I will begin by telling you something about me that is basically my background. So I'm Sicilian. I come from this beautiful island in the center of the Mediterranean Sea. And I'm an island indeed, I think it's a good definition. And after doing my PhD, my master and my PhD in Sicily, I started to do research in several countries, traveling from South Africa to Bulgaria, to Germany, Austria, and then Finland, the UK, and so on and so forth. So I've been moving quite a lot, and now since 1.5 years, I'm back in Turku, where I was for 5 years as a postdoc. And I was thinking in which way I could talk about beauty in quantum physics. And I actually, something that came to my mind is an experience that is not about quantum physics, but it's quite recent, and I want to share with you. This is something that happened this week. So I was with a friend of mine, someone I really deeply love, and in a beautiful setting. A very nice villa by Lake Nuxio, not far from here. And in the kitchen, he was cooking some, what I call orgasmic lasagna, because it really describes perfectly the type of lasagna that he can make. He was cooking lasagna for me, and I was close to the stove, actually close to the fires. So I was here, the fire was here, where he was cooking first some tomatoes, and here, exactly there was a window, beautiful, looking outside, and there was a day like this, one with sunshine, and with all these leaves falling, and the sea, I could see the sea. And I had in my hands a small piece of aubergine that he had cut. And I was touching this, it was cold, and I could feel the seeds. So I was exposed at the same time to this amazing landscape outside, beautiful, beautiful sunshine, and I was listening, not listening, but smelling this fantastic, beautiful smell from the tomato sauce. And he was next to me, moving, because he was moving from here to here. He was cutting something for the lasagna. And so I was feeling him. The act of cooking for someone is something that contains a lot of love. And I was listening to some music that I even have here. And I will, let's see, this works. You will hear it too. Obviously, in this case, it never works. Okay, let's see. Yes, okay. So, for a moment, imagine this thing. Imagine this immersion in all these senses. This music that for me means a lot, this person that for me means a lot, and I can see his love, really see. And then looking outside, the touching of these seeds and cold texture, and the smell that comes from the cooking. And it was perfection. And the only thing I could say was, this is so beautiful. And the reason why I'm telling this now is that although you cannot certainly feel what I was feeling, I have some words to describe to you experiences that you can connect to. Okay? experiences like love, experiences like, you know, this amazing smell, the cooking, experiences like watching something beautiful, because we all have shared, we have this common background. And now I have to make a step, okay? And I have to go and start talking about something for which we do not have, not only we do not have a shared language, but also we don't have any experiences of. Quantum physics is not something, the behavior of microscopic particles is not something that we have ever experienced. That it's not part of our logical way of reasoning, it's not part of our reality, it's not part of anything that we could ever imagine. So it's quite a challenge, but I will try. So, I will begin with one of my favorite quotes on quantum mechanics. This is from Nobel Prize winner Tony Leggett. And he says that quantum mechanics is very much more than just a theory. It is a completely new way of looking at the world, involving a change in paradigm, perhaps more radical than any other in the history of human thought. A unique change of paradigm, and I truly believe this. What is quantum physics? Quantum physics describes the behavior of microscopic particles, and it is the most fundamental of all physical theories. I describe the cosmology of the early universe, the physics of human vision, the behavior and the structure of the nucleon, and the way in which superconductors, for example, work. So from the most fundamental deep principles like the birth of all the universe till the most sophisticated technologies. However, it is very bizarre, and there are several aspects or several ways or several phenomena that are quite paradoxical. For example, microscopic particles like atoms or electrons can pass through solid walls. This is not something that we experience in our daily life. And when people ask me to talk about quantum physics, of course I can say things like, you know, microscopic particles pass through solid walls, and we sort of have an intuition. We've seen a lot of science fiction movies or something like that. But to truly describe what this means, I would need to use this math.
Okay, like that.
And this is a point I will stress many times. And the point is that, in fact, the only correct way to talk about quantum physics is through mathematics. It's a language that, however, is not commonly spoken by people. Only some specialists speak this language, but it is the only way we can really correctly, truly say what it means that a microscopic particle passes through solid walls. This brings me to another point that I will return to some of these points time and again, and we have time to discuss also later, which is connected to actually the topic of these workshops, that is connections between science and arts. Because if we don't have a common language, but still we want to share, can we perhaps use in this sharing some artistic forms to convey the beauty or to convey, you know, some of the feelings related to quantum physics and to what else? And I truly believe that it is possible. It is for me very exciting. I'm involved in a lot of science and art projects. And of course, this doesn't mean that you, in this way, you know, you will have, you know, a tool to do research in quantum physics. Although the interaction between scientists and artists can be very important also for the scientists to you know, when you look at something from a different perspective, you can have completely new intuition that then can feed into the scientific research. So it is important. And hopefully it's also a way to share something, because you see, we saw before these pictures, for example, of this beautiful landscape, or I was trying to describe you my very deep experience of beauty. And one of the things that I experience, and I think all of you, is in front of amazing beauty, we also have some sort of need to share it. We want to share it. We want to share it with others. We need to share it. I mean, it's like you are in front of a beautiful landscape and you want to have someone next to you and to say, wow, amazing. You need to communicate it in some way. And so that's also a need that we as quantum physicists have. And you can imagine the difficulty in the attempt to formulate some thoughts about it and to find a way of sharing it. So, I will now touch on another related point, that is the fact that even in our job, we have the math, right, we can make equations and we can predict physical phenomena, we can describe physical phenomena. However, very often we lack any sort of intuition. We have all these beautiful formulas which are correct. They are really, quantum mechanics is one of the most successful theories. It has never been disproved in any way. So we have all these formulas, but we lack the intuition. And this often is a further difficulty in continuing the research. And there is one sentence that I think is probably related to this slide by a famous American physicist, Richard Feynman. And Feynman said, it's like having a car for which you can, you know something. For example, you know the speed of the car or the position of the car. You can even predict where the car will be, but you cannot picture the car. You just cannot picture it in your mind. You can predict some things, you have the math right, but you cannot picture it. Similarly, another deep concept of quantum physics that is hard to fully understand is the fact that one atom, one molecule, one microscopic particle, by the way, microscopic particles are the constituents of everything around us. One microscopic particle can be at the same time in two different positions. So it can be here and on the other side of the universe at the same time. Okay? This picture, I mean, I can only draw two atoms, but actually this is one. Okay? It's one in two different places.
At the same time.
At the same time. At the same time. And of course, one it's already quite weird to imagine it, but if you think that we are made of atoms, atoms are the constituents of our body, I mean, we are made of atoms, then if a quantum particle can be here and there at the same time, why we can't? Why can't I be here and there at the same time? Is there any physical law that prevents me to be here and there at the same time? Is it a question of principle? Or is it just that it's too difficult? You know, is there like zero probability, or there is like a tiny little bit of probability for this to happen? Because, of course, if it were possible, I could at the same time be in Sicily eating an ice cream and in a smoke sauna, in some sauna in Finland. This would be super cool. One of my two nations. At the same time, I could have two, you know? And how would it feel? How would it feel? You know, how would I experience this thing? What would my mind be? You know, how would I... And in fact, recent research on quantum physics says that there is, at least we don't find any reason why this in principle could not happen. This problem is connected to something, perhaps the holy grail, you know, of quantum physics is called the quantum measurement problem, or also the quantum to classical transition, or the quantum classical border. I've tried to explain it in simple words, but the main idea is the following. You know, quantum physics describes very small particles, but as we progress with technology, we are able to control and to put in a quantum state bigger and bigger objects. So there are, for example, recently, researchers have built a quantum superposition of a tiny mirror, which is visible to the eye, actually, or visible to the eye, you have to have a microscope, but it's a tiny mirror. And they created a superposition of the mirror being still and oscillating. So as the technology progresses, we are able to manipulate big bigger and bigger object and to put them in quantum states and quantum superposition. So, I mean, the question is not trivial. I mean, we will ever be able to, you know, to increase this size. And the question is, where is the border? Where is the border between this fuzzy microscopic world, where all these strange things happen, and our world? You know, the world where this table is, where we are, where the projector is. Where is it? And we don't have a question about that. We don't have. I mean, we don't know. We don't know where this border is. We know that it depends on some things. Certainly, obviously, it depends on mass. The bigger is the object, the more difficult it is, you know, to manipulate or to put it in a quantum state. But we also know that it depends on time, funnily enough. Because in this experiment of the mirror being at the same time moving and still, you can create initially this peculiar quantum state, but it doesn't last long. So suddenly, or not suddenly, but with time, in a very short time, I'm talking about milliseconds, actually even less than milliseconds, the mirror becomes either still or moving. So you lose this property of the quantum superposition. So the border, this border is, we don't even know what are all the parameters describing the quantum to classical border, but certainly there is mass, so certainly there is time. And that's perhaps why we do not observe with macroscopic objects this sort of duality. Of course, this is clearly also related to, probably some of you have heard about this what was initially a paradox, the paradox of the Schrödinger's cat. Paradox of Schrödinger's cat. The Schrödinger cat is a Gedanken experiment, a thought experiment that was thought by one of the founding fathers of quantum physics, that is Schrödinger. And he said, if we apply the laws of quantum physics to any object, then I could imagine a situation in which these laws will predict that if I have a cat inside a box, and if inside the box there is also some poison, okay? It's in a bottle, a little bottle of poison, and this bottle of poison is connected to a hammer, and this hammer in turn is connected to a radioactive atom. Radioactive atom is an atom that follows quantum physics. If the atom emits radiation, then the hammer breaks the poison bottle, and the poison diffuses in the box, and the cat is dead. If the atom does not emit this radiation, then the hammer doesn't do anything, and the cat is alive. So the laws of quantum physics tell that if we don't look inside the box, if we let the system evolve freely, the cat will be at the same time alive and dead. And this is the prediction of physical theory, which is, you know, it's been confirmed. I mean, you should believe it as you believe in, I don't know, walls, or as you believe in taking an airplane, you know. I hate actually taking airplanes, but this is okay, so, because this is what the math says. But here there is another thing, provided we don't look. As soon as we open the box, we will always see either a dead cat or an alive cat. So what is the role of observation in quantum physics? And here with observation, I mean many things, and I will explain it in a moment. Well, one of the features of quantum physics is that microscopic particles may not possess well-defined properties like position. We imagine that everything has, you know, that there exists a reality, you know, independent from our observation, and that position in a specific point of space is something that exists independently from us. Okay? Reality exists independently from the observer. It's almost part of our, you know, system of thought. But microscopic particles may not possess well-defined properties until we look at them. When we look at them, they acquire a property like position. So the act of observation, this is mind-blowing by the way, because it means that the act of observation actually creates reality. The particle is interacting with everything around her. I will use the word entanglement, and I will explain it in a moment what it is. So because of the interconnection or entanglement between one particle and all the rest of the world, it's like if the rest of the world is observing the particle and therefore enforcing the position or the reality of the particle to occur. So it is because of this interconnected between everything that exists that reality emerges, as we know. So it's not just the act of observations in the sense of a conscious human being, but it's this entanglement between all existing things surrounding us. The phenomenon is called environment-induced decoherence, if you want to know. The specific technical term is the presence of this interaction. So I promised to talk a little bit about entanglement, and I'm doing it immediately, checking time, because I tend to talk a lot, especially when there's a patient about. And I will do it introducing the example of the bank robbery. It's similar to the Schrödinger cat, just slightly moving the discussion. The bank robbery. Imagine a bank robbery. Okay? There is a teller with some money, and a robber that points a gun to the teller. We are used to correlations, okay? We immediately understand that if the gun has fired, then the teller is alive. If the gun has not fired, then the teller is dead. This is a type of correlations that we are used to. Okay? However, if a quantum bank robbery would exist, then the gun could be again triggered by some quantum law. And in this case, the state of the teller would be in a superposition of being dead and alive. And this superposition is something here I'm using a notation that is what we really use. You see this we call this cats. It's actually a mathematical object. You can follow certain rules. This cats, it identifies completely the state of the atom, and this is everything that identifies completely the state of the teller. So the teller would be in an entangled state with the atom. Okay, so it's not just a superposition of being dead and alive, but there would be a special correlation between the state of the atom and the state of the teller. And if you imagine these to be two different atoms, for example, and you can bring them far away in the universe, this simply means that there is no specific, unique way of describing the state of the teller or the other atom independently from the other. It makes no sense to talk about the teller without the atom. I mean, they're one thing. They're really entangled. Two entangled particles or two entangled objects are one thing. There is no independent reality for them. So even if they are into different, physically, into different parts of the universe, anytime I would observe this one and see, for example, that the atom is decayed, then this superposition would be broken. And let's say the teller would acquire the property of being there. Okay. So this is what entanglement tells us. And this because of this entanglement between everything, somehow, that the objective properties in classical system. Now, perhaps I will talk a little bit about another new advance in quantum physics, because everything I said is quite deeply connected also to a lot of philosophical problems and to what we call fundamentals of quantum physics. But now there are new trends that are related to how to exploit these properties for technologies. And so there is a lot of research being done for what we call quantum technologies, that are technologies that exploit or use these specific features to build new devices that work in different ways. And I mean, you may call it as an applicative, if you want, applicative science, but it isn't, because in some sense it is, but in another sense it isn't, because at the same time we learn a lot also about the fundamentals of quantum physics. And the main application is quantum computers. And in fact, it's an interesting open question whether a real quantum computer can be built, but what we have learned has to do with the if you want, translation or reinterpretation of these concepts in terms of information theory. So what has happened is that information theory and quantum physics came together to form a new field, that is quantum information theory, and this has changed the way in which we describe also quantum physics, because now we use more information-related approach, you know, to describe physical systems. So this is, if this could be the internal part of a computer like the one I have, what would be the analog for a quantum computer? Well, first of all, the translation of the classical concept of a bit is a unit of classical information. It's a dualistic thing, 0 or 1. All computers are made manipulating this a bit of information. It's the minimum amount of information that you can have, 0 or 1. And the analog in the quantum case is a qubit. But of course, as you understand, as I mentioned before, if a bit is either 0 or 1, a qubit can be 0 and 1 at the same time. So how does this change the ability to process information? And it turns out that it would change dramatically. The reason why it would is because there are certain problems that are not solvable with classical computers, with our computers, okay? So, let me put it this way. Mathematics is the language we use to describe the universe, we as scientists. We use mathematics. Mathematics there is a quote by Galileo Galilei saying that mathematics is the language in which the universe is written. Mathematics is the language in which God speaks, he was saying. And the reason of this is because we don't know why, but we do understand the physical phenomena, nature, and the universe in terms of mathematics, mathematical formula, and we use this mathematical formula to predict and create technologies. Okay? So it's because of mathematics that we have airplanes, cars, these buildings. We build them because we have mathematics. We can make formulas and create things, which is technologies. It's the language we speak. And also the same language that we use to understand physical phenomena and the nature. However, not everything, apparently, is calculable, we say. Not everything can be calculated using computers. You know that nowadays we live in an information area. Everything is related to the speed at which we process information. Everything we do with our mobile phones, our computers, is related to how fast we can process information. And there are systems, like quantum systems, that cannot be studied with any classical computer. And it's not because of technological limitation, it's because of a fundamental reason. They are beyond our ability of calculus. Okay? For example, already a system of 500 qubits cannot be, so if we would use the base computer existent today, it would take a time longer than the age of the universe. When we say that it's not computable, we normally relate this to the age of the universe. It would require time longer than the age of the universe, so we can't do it. And instead, a quantum computer would be able to make these calculations because it's quantum inside. So it exploits this parallelism somehow. It exploits this presence of the superposition. So it's like if you can evolve, if you can make a calculation using in parallel a superposition of many qubits. Okay, so it is really not just more powerful, it's a different fundamental mode of computing. Okay. However, you have this problem that is the readout problem that is related to what I talked before of observation. Okay? Because, well, it's true, a quantum computer could process much more information, simulate, I don't know, the whole universe. However, at some point you need to read it. You need a readout. You need to check the result of the computation. And the moment you check it, you destroy quantumness because you destroy what is quantum inside. So, nice, it would be like a box that you can't look. So apparently, is it really useful? How can we go around this? And in fact, there are ways to go around. There have been discoveries of quantum-based algorithms that use this entanglement property. So basically what they do, it's like, we call it choreographing interference. So it's like if you use entanglement, you don't watch at the beginning, you use entanglement and certain answers interfere, it's very difficult to explain it, and at the end, only the correct answer comes out. So it's a difficult way, difficult thing to explain. But you can use this entanglement between the different, not just the superposition, this parallelism, but this entanglement to somehow, actually go around the readout problem. So you will read out, you will change eventually the answer, but because of the way in which the algorithm is structured, you will still have a time advantage with respect to the classical ones. So in principle, they are existing. Are there quantum computers in the labs? Well, there are some. We do have in the laboratory some small quantum computers, but they are quantum computers of few, like, 16 qubits. There is a company called D-Wave that can sells actually quantum computers. I think the biggest they have is 512 qubits. And it costs, recently, Google and NASA bought one of these quantum computers for the cost of $10 million. It costs $10 million if you want to have a quantum computers. But the community is skeptical about actually the quantum is inside, they are black boxes. So quantum computer, yes or not, we don't know. We do not know.
At the same time, it works.
Yes. We do not know, however, the question of whether quantum computers may or may not exist is tightly connected to one of the most fundamental questions, that is, whether there are ultimate limits of what can be feasibly computed in nature. Is there a limit of what can be feasibly computed in nature? And this is at once a philosophical, a scientific, and, So a philosophical, a scientific, and of course a practical and technological question on which a lot of people are discussing and doing debates about. At this point, I would like to show you a small video, a short video of Richard Feynman talking about our difficulties in understanding quantum physics and whether they are fundamental or not. And I think that this probably will work now, the audio. Let's see.
That little thing behaved very differently than anything that was big. Anything that you're familiar with. Because you see, as the animal evolves and so on, as the brain evolves, it gets used to handling, the brain is designed for ordinary circumstances. But if the gut particles in the deep inner workings were by some other rules and some other character, they behaved differently, they were very different than anything on a large scale, then there would be some kind of difficulty in understanding and imagining reality. And that difficulty we are in. The behavior of things on a small scale is so fantastic. It's so wonderfully different, so marvelously different than anything that behaves on a large scale. You say electrons act like waves. No, they don't exactly. They act like particles. No, they don't exactly. They act like a kind of a fog around the nucleus. No, they don't exactly. And if you would like to get a clear, sharp picture of an atom, so that you can tell exactly how it's going to behave correctly, and have a good image, in other words, a really good image of reality, I don't know how to do it. Because that image has to be mathematical. We have a mathematical expression, strange, isn't it? Mathematics, I don't understand how it is, but we can write mathematical expressions and calculate what the thing is going to do without actually being able to picture it. It would be something like a computer that you put certain numbers in and you have a formula for at what time the car will arrive at different destinations, and the thing does the arithmetic to figure out what time the car arrives at the different destinations, but cannot picture the car. It's just doing the arithmetic. So we know how to do the arithmetic, but we cannot picture the car. No, it's not 100% because for certain approximate situations, a certain kind of approximate picture works. That is simply a fog around the nucleus that when you squeeze it, it repels you. It's very good for understanding the stiffness of material. that it's a wave which does this and that is very good for some other phenomena. All right? So when you're working with certain particular aspects of the behavior of atoms, for instance, when I was talking about temperature and so forth, that they're just little balls is good enough, and it gives a very nice picture of temperature. But if you ask more specific questions, and you get down to questions like, how is it that when you cool helium down, even to absolute zero, where there's not supposed to be any motion, it's a perfect fluid that hasn't any viscosity, has no resistance, flows perfectly, and isn't freezing? Well, if you want to get a picture of atoms that has all of that in it, I can't do it. But I can explain why the helium behaves as it does by taking my equations and showing the consequences of them is that the helium will behave as it is observed to behave. So we know we have the theory right, but we haven't got the pictures that will go with the theory. And is that because we're limited and haven't caught on to the right pictures? Or is that because there aren't any right pictures for people who have to make pictures out of things that are familiar to them? Well, let's suppose it's the last one, that there's no right pictures in terms of things that are familiar to them. Is it possible then to develop a familiarity with those things that are not familiar on hand by study? By learning about the properties of atoms and quantum mechanics, by practicing with the equations,